Hi everyone, I'm Xiangwei. I'm from Delft University of Technology. So today I'm going to present our work, WeightAlign, Normalizing Activations by Weight Alignment. So the first part is our motivation. In the field of deep learning, batch normalization is widely used in neural networks. It allows training very deep networks and accelerates training speed. It normalizes the activations by mini-batch sample statistics. So when the batch size is very small, the performance of batch normalization will be very unstable. Therefore, we proposed WeightAlign, a method normalizing activations by reparameterizing filter weights instead of using sample statistics. In this way, the performance of WeightAlign is stable and independent of batch size or sample statistics. So now let's look at the method overview. This graph shows the working flow of WeightAlign. During each forward pass, we have activations from previous layer, which is Y here, and the weights W. The weights W has 4 dimensions. They are convolution filter size K by K, the number of input channel C, and the output channel C out. We take the weights from each filter. We can see here the size of a filter is K by K by C, and the total number of filters is C out. We then align and reparameterize the filters' weights and make their distribution satisfy a zero mean and unit variation distribution. With the effort of a learnable scale gamma, we can normalize the output activation X. Next, let's dive into the proposed methods briefly. We know batch normalization normalizes the activations in a single channel to a zero mean and unit variance distribution, and scale and shift the outputs by using equation 1. And we can see the sample statistics of mu beta and sigma beta here represents the mean and standard derivation of activations X. We can also express these sample statistics using weights, like equation 2 and 3. Because of convolution operation, mu beta is the product of filter size n and the expectation of weights W and the expectation of activations from previous layer Y. And we can see the sigma beta square can be written in equation 3. So as long as we keep the expectation of weights 0 and the variance of weights constant, we can still force the distribution of activation X to a zero mean and unit variance distribution. So therefore, WeightAlign reparameterizes the weights using equation 5. And here, the gamma is a learnable parameter. In this method, no sample statistics is used, and the cat W is the new weight to get the normalized activation X. So next is our experiment results. We first visualized single channel activation distributions during training. We trained 6 different networks, and they are baseline using WeightAlign, baseline with batch normalization layer, baseline with layer normalization layers, baseline with instance normalization layers, and baseline with group normalization layers. And we can see this dimension represents the values of activations, and this dimension stands for the training epoch. We can easily get that the distributions of activations using WeightAlign and batch normalization are nicely symmetric around 0 compared to other normalization methods and baseline. And this table shows the errors on CIFAR 10 for classification tasks. We can see that WeightAlign is comparable to other normalization methods regardless of batch size, and helps the performance when combined with other normalization methods. We also do the classification task on ImageNet dataset with different network structures. We can see the performance improved when combining WeightAlign and batch normalization. We also compared WeightAlign on other tasks like semantic segmentation and domain adaptations. If you are interested in the details, please and welcome to look through our paper. That's all. Thank you.